Hi, folks. Welcome back to part 3 now. We're going to talk about the social networks and health didactic session recordings. And we're going to spend now a little bit of time thinking about models of networks and health. The plan today is to, again, I'll try to give you this a brief introduction to some of the key elements of the what and the why of these things. We're going to start with diffusion, which is sort of the root of the connectionist models of networks we've been working with. And we're going to talk about two substantive elements of diffusion through networks. The first one is disease diffusion, which is relatively poignant given all the work we're doing currently on COVID, and how that then really provides us the groundwork to then think about network autocorrelation models, or peer influence models is the other language for those. Once we get to those, you're going to realize that it sort of leaves us with a bit of a problem we have yet to solve, which is that, particularly for networks and health, we care not only about the network itself and what moves across the network, but where the network comes from, because we need to know that in order to disentangle this, what's called the selection of influence problem. So we're going to talk then about a way of doing that. But to get to that first, we need to understand where networks come from, and so we're going to introduce random graph models. Now, random graphs are an entire field of their own right. There's a whole lot of work we can do this, and we're not going to do a technical version of this. We're going to really try to give you an intuition about the ways in which graphs can be understood. And the key thing to take home from here is that thinking about models for graphs, models for networks, your intuitions about the way coefficients and models work for linear processes, sort of a little bit of y gives you a little bit of x sorts of models that we're used to from the general linear model don't really work here. These graphs can be highly nonlinear, and they do things we just don't really intuit very well. So I'm going to ask you to trust me on that. I'm going to explain to you how that works. That's going to provide a foundation for us then to move into being able to answer this diffusion or this selection or influence problem to the extent to which it can be answered. And we're going to propose two ways of doing that. The first is through experiments. And I'm just going to point out to you what experiments can do, because I think it helps to think like an experimentalist when you try to evaluate statistical observational models of network outcomes. And then we're going to talk about stochastic actor-oriented models. That should be an SAOM. Not an SOAM, sorry about that. I'm not going to redo this to do that. So anyway, the plan then is to talk about these stochastic actor-oriented models, or Siena models, and then finish up with a set of open questions. All right, let's get started. All right, so the primary route from networks to health is via diffusion. Either a pathogen, like we catch a bug, we sneeze on our neighbors, and that creates a COVID pandemic that shuts down the globe. Or I tell you something about what is good for you, you believe it, and then you change your behavior, right? So either way, we're going to talk about diffusion of either an information or a pathogen moving through a network. We're going to start with biological diffusion, because it's the clearest example of the way these things work. And once we know that example, it becomes easier to talk about social diffusion. All right, so the classic, I'm going to get my pointer here again, the classic diffusion model is known as the compartmental model from epidemiology. And here you can imagine dividing your population into a series of compartments. And those compartments are defined by your status on the disease in question. So you have a susceptible set and an infectious set, and in what's known as a susceptible, infected, susceptible model, then you move from the susceptible set to the infectious set. With some probability you recover and you become susceptible again. So this is the SI back to S model. Slightly more complicated model, you could be susceptible, you get exposed to the disease, it cooks in you for a little while you're exposed, and then later you become infectious. You have your infectious for a while, then later you become recovered, and you may or may not come back to susceptible. So alpha could be 0 if it's an SIR and stops, like everybody goes to this recovered state. Now, the beautiful part about these models is that these are literally just mass action transmission models, right? So it's the case that you find yourself in a particular state. There's some probability that if you're in that state, you transition to that state. Given that you're in this state, there's some probability that you transition to the next state, and so forth. And the beautiful part here is that once you understand what those probabilities are, you can write them down. And so the change, right, the change in my likelihood of the number of infected people in the population is just a function of the number of this parameter times the proportion of the population that's in that state. subtracted from that the people who have moved out to the other set. And so it becomes really nice to be able to write these down as linked differential equation models, where you have this probability of moving from one set to the next. Now these models end up making they work well, and they're nice to write down, and they're sort of mathematically beautiful because they make really strong assumptions, right? And so if you assume that everyone in this state has the exact same probability, like that's what it means to be in this state, is that everyone here is equally likely to move from the other set. If that assumption is not true, then you need some other state, right? You need to have a finer, smaller compartment that you can put people in, such that you can apply these homogeneous simple mixing parameters. And the general notion of network models and network epidemiology models is that it's rarely the case that these kinds of assumptions are accurate, that it's usually not the case that it's just enough to say that there's a simple single parameter that's going to apply to everyone who's susceptible to the disease, this thing going to lead them uniformly in lockstep to the next outcome and so forth. So instead, we either have some amount of randomness, and that we can deal with stochastic versions of these models, or we have some other element that leads to heterogeneous parameters, particularly network parameters, right? So we think that about a network version of these models, we want to think about what are the features then that contribute most to the potential for something to move through a population, for a biological bug to move through a network. And it turns out that we can divide this problem into three different parts, but we're going to hold one of them constant. So that is, in addition to the dyadic probability that one actor passes something to the other, this is what I'm going to call PIJ throughout the rest of this description. That's the one thing we're holding constant. We're just not going to think about that right now. So, but in addition to that, what does a network bring to the spread of something through a population? The two features we want to think about are the topology of the network, that is the shape, these reachability, connectivity, and distance features that we talked about before, or redundancy, connectivity, and distance, or the timing of relationships. And we're not going to spend much time talking about this, just to be honest. I'm going to go over that pretty quickly today. But the shape of the network, it helps us see whether or not it's likely that things move quickly or slowly through the network. And we'll talk about what those are. Just to build a little bit of quick intuition. So here's the same basic kind of setup, right? So we have a real network and a random network, and that's the difference between the kind of compartmental model versus a network model. So for a compartmental model, we assume that essentially people have an equal probability of bumping into everyone else. It's no different than a random graph. It's just that I just randomly choose people within my compartment because they're all substitutable. They're all equally the same. In a real network, that's not the case. We have these clusters of people, and those clusters are going to make it more likely that I give my disease to somebody else in my cluster than to somebody who's not in my cluster. And that's going to matter for the spread of the disease. So for example, if we take this example network that I just showed you here, if I start with this node as my seed node, so this node enters the population with the disease, then we flip a coin at each time step to say how many of their neighbors do they infect. Well, depending on what that probability of infection is, you can either have a really low curve or a really high curve. And that probability is defined by the structure of this network. Now, there's some basic randomness to this, of course, right? So that same set, if I flip that coin 1,000 different times, like PIJ does matter, right? That's going to be the thing that really governs this set. But it's interesting for us that there's a lot of variability inside these networks or inside these curves. And that variability is governed in large part by the pattern of ties within the network. So what are the features that govern that spread? It turns out that we can think of 5 sort of key elements within the topology of a network that determine the likelihood of spread of a pathogen, a stochastic spread of a pathogen through the network. The first thing is this combination of reachability and distance, and I'm going to put them together here and focus on distance really. And so given that it's the probability that I can reach you, the probability that I'm going to pass my bug to you in the network is going to depend on how far we are from each other. This is really easy to think about, right? Because if the probability of transmission is anything less than certain, then at each step along the chain, what's happening is I'm flipping a coin. Right? And if that, so the probability that it makes it 1 step is going to be PIJ. Probability that it makes it 2 steps on that chain is going to be PIJ times PIJ and so forth, right? So you're going to get and of it going through, and that necessarily decreases with the number of steps in the network. Now, the other thing that then governs this is going to be this local clustering. So given the number of ties that go out from me, do they reach new people or do they reach the same people? And so if I have lots of, if each person has a binary split, in this case, I have 2 ties, this person has 1 tie, but you can see how it splits out. If I'm reaching new people at each step, then it's possible to reach a lot more people than it is if that same tie comes back to the other person. So in this case, I have a lot of these local redundant ties, this local clustering. That means that I don't reach lots of new people. So all of these people in the network never get reached in this spread of the network because the local clustering turns the tie back on itself. This is a really important point because what it means is that diffusion has this clustering really plays 2 roles in the network. We're going to see this in a second. It plays this role on the local hand of limiting the number of new people you can reach. So if Pij is really high, if the probability of transfer is really, really easy, then weak ties and low redundancy mean I can spread and reach many people quickly. If it's really hard to spread the disease, then this local redundancy ends up creating a robustness effect. So there's a split return to local redundancy depending on how high the probability of transmission is at any given point. Okay. And this then takes us to this notion of alternative routes. And so if you have lots of, remember we just said that if you have a single path from one person to the next, it's a function that the probability of transmission is a decreasing function of distance. And this is just because you're multiplying paths many times. But the flip side of that is that if you have lots of paths, then you end up with lots of alternate routes. So that is, I can go down this path, or this path, or this path, or that path. It's the difference from multiplying probabilities versus adding probabilities. And so if you have lots and lots of paths, then you're nearly certain to pass the disease off or whatever it is over a short number of paths. Okay. This is what takes us back to this idea we described in the last section on structural cohesion. And so the reason that structural cohesion matters in networks and health is that that's what's creating these multiple routes. And so it doesn't matter if we're talking about HIV, for example, if one person is using a condom in this network over here, because even if this person is consistently using a condom for an HIV spread in this network, you can always find a way around that node. Whereas in this network, it's the case that if this person's using a condom, there's no way that the disease is going to get around them to the other set. So this is why this node connectivity matters. It creates a redundancy in the network. That means that the spread of a pathogen through the population is never dependent on a single person because it has the opportunity to go around. As an example of this, returning to Colorado Springs, you've seen the graph on the left multiple times. This is the sexual network in Colorado Springs. There is a core of this network, this is a 3 core. So everybody in this network, in this yellow set, there are at least 3 node independent paths connecting every other person in this set. That means that if an STD were to reach this set, you need to have almost uniform use of condoms to ensure that there's no passage of the good. Because if any one of the 3 possible routes around you fail, then the disease is going to move around. And so this core in the middle is a highly likely. Now, the thing to point out is that there are nodes in this 3 core that are not commercial sex workers, right? These are nodes that are bridges between commercial sex workers. So it's not just degree, right? In order to be in a 3 core, you have to have at least 3 ties. That's a defining feature, but you don't have to be one of these nodes. In fact, there are lots of nodes out here that are commercial sex workers that are not part of the structural 3 core. On the other hand, if you look at the drug sharing network, and they've laid them out roughly in similar positions, you can see where they're at. You have not just the nodes that are reconnected in the core, but you have these cliques. And this is because the social behavior of drug sharing tends to be much more community oriented as opposed to individualistic. Right, so sex is a relatively dyadic engagement, whereas drug sharing networks tend to be done in groups, at least in this time in Colorado Springs they were. And so you get these heavy cliques. What that means is that you have lots of opportunities within these cliques for for disease to pass, and this is part of the reason that drug sharing, needle sharing, ends up being such an awful way for diseases to transmit, because it's just such a robust underlying network. There's so many alternate routes through which the disease can flow. In addition to, of course, the feature that when you're sharing needles, in particular, you're also breaking the blood barrier, so you end up with a higher dyadic transmission probability. Multiply that by the fact that you have all these alternate routes, means that you end up with a really high probability of transmission through needles, much higher transmission through needles than through HIV than through sex. All right, so that's just to give you a sense of the underlying importance of redundancy in these networks. The final element in terms of the topology that, is this the ability for there to be star spreaders. And this gets back to an idea that we briefly touched about in the last section on power law distributions or long tail degree distributions. If there are nodes in the network that act as hubs, those hubs can reach lots of people and they create these connectivity sets. So if it's the case that a single node is there, it can act as a bridge to lots of other sets if it's one of these tail nodes. If it's a node that's on the end, it has the high probability of spreading to lots of others. This happens, by the way, based on the degree correlation. So if you have an assortative network, that means that high degree nodes tend to hang out with other high degree nodes. That'll give you a core and a periphery kind of setting, whereas a disassortative network means that high degree nodes tends to connect with low degree nodes. Disassortative networks are characteristic of sexual networks, commercial sex networks, where commercial sex workers have lots of partners that are not necessarily reconnected with everyone else in the network. Assortative networks tend to be more organic in how they come to be, and you have a case where people who are wallflowers tend to hang out with other wallflowers, academics with other academics, commercial sex workers with other commercial sex workers. That's a bad example. But they have very different diffusion features. That one of the things about assortative mixing is that it does tend to create lots of global connectivity, whereas disassortative networks creates lots of star spreaders. And so they're very different kinds of risk environments. Now, this might give you a sense then a little bit about where this connectivity came from the example I gave when we were talking at the very beginning of these discussions about position of small nodes. We're returning to that here. This is that graph I showed at the very beginning where we can think about the spread of a disease through a network. Given a low degree network, you can end up with these networks that have very little connectivity, right? And then a little bit of change in the degree distribution, you get networks with very high connectivity. That happens because of a feature of random graphs. And as you might imagine, I didn't pick those 4 networks at random. I picked them because they're right on the edge of this thing, which is known as a phase shift. And a phase shift happens in random graphs when you move from largely disconnected network and then rapidly flip over to something else. In this case, you go from almost being everyone disconnected, right, to everyone in this regime, everyone is connected. And that's what this blue line captures, is the number of people who could ultimately reach everyone else in the network. This is a characteristic of graphs. And then when I told you at the very beginning that you want to sort of set aside your intuition about the way things change, you get these very nonlinear shifts with a small change in the network. So again, going from a 1.68 to 1.87, you move from almost nobody connected to everyone else and nobody connected in terms of a bi-connected or 2-path opportunity to almost everybody connected in a 2-path. And so this notion of having a rapid reconnection through this set happens even a very small change in the degree distribution is an example of one of the kind of nonlinearities that happen. The other thing that sort of happens here is that this is a kind of super sharp shift is happening with these low degree networks here, right, where no one has more than 3 ties. If instead we keep the same average, but spread out the tail, so now we give some of that volume of that network to a few people who have lots of ties, you still see a phase shift. It's now shifted over here to the left, so it happens at a lower degree, but it's not quite as steep. So it's still pretty steep. You go from nobody connected to about half the people connected over a 0.2 shift in average degree, but it's much smoother than it is with this low degree. And that's because when you have a star network, you can sort of take in little pieces of the network at the time and connect to that star. Whereas when everyone is little, it's kind of like having lots of little chunks build up, and then all of a sudden one tie will pull those chunks together, which then pull bigger chunks together and bigger chunks together. And so you get these rapid shifts with low degree. And that's a little bit counterintuitive. People tend to think that this is the most dangerous world when you have these long tail distributions with some people engaged in lots of activity. A lot of our policy activities are focused on commercial sex workers because that's where this huge volume is. But it turns out that that's not really the spot that's going to, from a mathematical standpoint anyway, that's not the spot where you're going to see the biggest shift. You're going to see it over here in these kinds of networks that look innocuous at the local level, but when you put everyone together, you get a global shift that's outcome. And there's some evidence that this is characteristic of this movement from a network where you have a long tail and a smooth transition to a giant component, and a short tail and a sharp transition is a little bit of what happens when you chase the tail away. So if you really focus on commercial sex workers, for example, in terms of the people you're going to focus your attention on, you might distribute the demand for sex in a way that creates more actors engaged in less, and each one engaged in less activity will create situations where you have these shorter tail distributions. Anyway, it's something to think about just intuitively about the ways in which the shape of the network is going to emerge in ways that you might not expect otherwise. All right, if we shift the second feature that matters for networks in terms of diffusion is the timing of relations. And there's a bunch of work on this. I don't have time to go into it into great detail, but I want to spend a little bit of time thinking about this for us. I'm also going to shift over here. Let me just do, right, okay. Just a second here. Okay. So imagine then, we have a network. I want to explain a little bit first about what I mean by the timing of relations. So when we think about a dynamic network, the notion here is that edges aren't always on or always off. Instead, we have relationships that unfold over time. So in this case, this little toy example, we have person A and B have a relation that started and ended at the second time step. And this one started and ended at the third time step. So if A has a series of relationships, early, later, latest, this one happens after that, this one happens after that, and I've just added time steps to them in single chunks. If you think about how things spread through a network, they can only spread downstream in time, right? So you're only at risk of spreading a disease forward through your network, not backwards in time. So you can't infect a past partner, you can only infect a future partner. So in this case, if you imagine person A could infect person C at time 4, person D at time 3, person 2 at time 2. Now, if you go to person 2 at time 2, then later at time 5, that infection could reach person J. At time 6, it could reach person M. So person A can reach all of these people downstream, but can't reach any of these people because this relationship happened at time 1, this relationship happened at time 3, so this relationship happens after this one ends. And so timing creates these breaks, and these breaks mean that there's a subset of edges over which it's possible for an exposure to happen. Concurrency is one element of this kind of overlap in time. So two edges are said to be concurrent if they overlap in time. And I give the formal definition here. It's easier to see graphically. So if you imagine the AB edge started at time 1 and ends at time 3, the BC relationship starts at time 2 and ends at time 8, the CE relationship starts at time 5 and ends at time 7. If they overlap in time, they're concurrent. So the AB and BC are concurrent, and BC is concurrent with CE. Concurrency is a feature of an edge. So edges are concurrent. People can have concurrent relations, but it's a characteristic of the relationship, not of the people. This ends up being the case that, no, I'm not going to go into that. Now, one of the things that's interesting about concurrency is concurrency creates a gate on the timing of relations. And it means that a lot of things that we might imagine happen in a network don't play out quite the way we would expect. So it's the case, for example, that A can reach C, but it's not the case in this network that C can reach A. So the kinds of transitive and reciprocity that you expect from simple graph theory, you think that if A can affect B and B can affect C, that and C can infect B, you would think that C could also infect A, but it doesn't work out that way because of the timing of relations. And so this kind of asymmetry that timing puts into the network really creates some interesting features on the graph. The thing that concurrency does is that concurrency creates two-way paths in places where there would otherwise only be a one-way path. So this is a nice little simple example. Here's the same exact contact structure. A is connected to B and B is connected to C. If these things do not overlap in time, then A could infect C, but not vice versa. If they overlap in time, then A can infect C and C can infect A. You might think, no big deal, right? You get, instead of a single arc, you get 2 arcs, who cares? The reason you care is that A is going to have future partners downstream in time that prior to this happening, right? In this situation, C can infect none of A's future partners. There's never any downstream risk that comes from C's relationship or potential to expose A. But once you create this concurrency, now the entire sort of wing of relationships that A might have in the future are at risk to whatever C brought into the relationship with B. And so this gatekeeping function of time, what concurrency does is it opens all of the floodgates and it makes them possible to go everywhere, whereas before they used to be constrained. Okay. Just to give you a sense of that, a concurrency has this feature. And so I want to give you a sense of which this timing matters. This is the exact same contact graph. So we're with the contact ties in red, the infection exposure ties are in black. So it's possible then, given a contact structure in a ring, if all the relationship happened at the same time, then everyone could reach everyone else. A could reach everyone either clockwise or everyone counterclockwise. So there's 2 indirect paths between everyone else. Now, if I put timing in this relationship, we see that person 1 has this relationship at time 1, at time 2, at time 3. So person 1 can reach everyone else in the future, right? But person 8 here can't reach any of these other people, right, in time, because this was the last relationship that happened. So this person's at risk to everyone upstream, but no one's at risk to this person, even though the contact structure remains the same. And you can play games with this timing, right? You can see that there are different timings depending on when you put them in the network, right? When these relationships happen, lead to different exposure risk for the population as a whole. And so the exact same contact structure, that is the exact same pairs of people in the adjacency network, can create radically different exposure networks and thus radically different epidemic sizes depending only on the timing of relations. And it's really important to point out that this is a population level feature. This is not an individual level feature. It doesn't matter for each individual here still has 2 partners. So at the local risk standpoint, there's really no difference, but there's a strong risk change at the global population level because of a change in the ways that these, these relationships unfolded in time. This then is a way to explain that graph I showed you earlier in the visualization set. These are concurrent relationships, the ones in red, and these concurrent transmission trees are ones that are like that CD relationship there before, where the one's embedded within the other. Those are backward concurrents. They would have, nothing downstream would have occurred had it not been for the concurrent relationship upstream. And so concurrency creates these open gates that would not otherwise have allowed an infection to flow through. Okay. All right. Timing constraint is one kind of a sort of layer, a positional layer on the graph, is when relationships happen. Another way of thinking about the way the graph structure might be modified for diffusion is the way to think about something that we call complex contagion. So complex contagion exists when you have a rule for the ways in which something diffuses that say that it's not dependent only on something that has to do with that single dyad. So for most diseases, it's the case that I get the disease from a single person and it doesn't matter what the rest of my contacts are. For social diffusion, that might not be the case. And for social diffusion, it could be the case that I only decide that I'm going to get the vaccine if at least 2 of my friends have also got the vaccine. And so the notion of believing something or having something pass through a social network, it's possible that I'm going to have a threshold upon which to adopt something that's going to depend on the number of people who have engaged it. And so Damon Centola has coined this notion of complex contagion that says that ego is only going to adopt if many of their alters adopt. And that is an important thing to play with. The idea here is something like this, right? So imagine that these 2 folks are infected at time 1. They can't infect time 3 because person 3 won't adopt the network because only one of their neighbors at time 2 has done it. At time 2, these folks get it. And then once all 3 of these are gained, this person has 2 neighbors that engaged. Notice the infection would never pass over to these, for I shouldn't use infection. The adoption would never pass over to these sects, because these folks never have an opportunity for 2 of their neighbors to have had it. So complex contagion is a nice new idea. It leads to some interesting dynamics. For those that are really interested, I encourage you to look through some of the slides. It leads to some outcomes that you wouldn't have expected otherwise. I'm not going to go through it in great detail, just in the interest of time, but it is kind of a fun way of thinking about it. So biological diffusion, complex diffusion, timing, these are all layers on a bit moving through the graph. The key thing that distinguishes peer influence models and social diffusion from biological diffusion or some of these other mechanistic diffusion models like adoption models are that we expect that the thing that diffuses through the network doesn't do so mechanistically. It has some sort of mutability as it moves through. So I don't believe exactly what you believe when I sort of hear a rumor from you, or sort of you influence me in my behavior. Instead, you change my mind a little bit. And so where the thing that's moving through the network is typically continuous. And so we want to think then a little bit about the ways in which my behavior moves through the network. And to do that, we're going to use a network autocorrelation model. The network autocorrelation model, where do I have this here? Is here. Okay. So we're going to spend a little bit of time on this. This is building on a great book called The Structural Theory of Social Influence. I strongly encourage you, if this is an area you want to play in, I'm going to go and find this book and read it. It lays out these things in nice detail. The fundamental idea here is that any person's behavior is a function of 2 sources. On the one hand, you have individual characteristics, right, that are your classic attribute driving behaviors. So it might be my gender, age, race, etc. Drives the behavior that I engage in. And because I'm a white older male, I do one thing which would be different than if I were a young female of color, right? So these things all change our attitudes and our behaviors and beliefs. In addition to that, there's some element of interpersonal influence, that the people I engage with and act with, those people convince me to do stuff or change my beliefs about things. And I negotiate my beliefs and understanding with others and come to a new understanding, and that builds itself up. What's nice about thinking about it as a 2-part model is you can write it down as a 2-part model. So that first part here is that at time 1, that is at some initial primordial time, my understanding, my belief about or attitude about the outcome is a function in a classic regression sense of my attributes and a set of coefficients. And then at time t, it's a function of my initial set at time 1, plus this feature, which is an interpersonal influence matrix and my friend's behavior at time t minus 1. Those 2 features, my initial individualized response and my peer response, are balanced by this peer influence coefficient. So it's alpha and 1 minus alpha. The key element that drives this is this W matrix, this weight matrix. And this is an n by n matrix of interpersonal influences. This is effectively a function of the adjacency matrix. And I'll show you how you get from adjacency matrix to this in a moment. All right, so how do we make sense of this? First, we need to have a couple of constraints that are effectively assumptions of this model. The first is that the weight matrix is bounded by 0 and 1. What this does is this means that the opinion belief doesn't expand beyond the range of the original range of opinions. Similarly, it sums to 1, so this is going to mean that I never get greater than 1 outcomes. And this again is just these 2 constraints just ensure that the belief model becomes what's known as a consensus model. Your new time 2 opinion will always be bounded by the range of the time 1 opinions. Some formal properties of the model. It's kind of I have some more slides in the deck if you want to go through and look at them. They're hidden here in this piece, but you're welcome to go and dig into it in a little greater degree. A key element of this is that we can substitute this out, right? So we just have our regression effect and our peer influence effect. At equilibrium, right, if you let this model go and go and go, it's going to converge. And what it converges on is that a coefficient times the peer influence outcome times the same thing, right? So notice that y at equilibrium is on both sides of the equation here. this is really telling me that, I've taken the dependent variable, I've weighted my peers by it. So stop for just a minute if you remember your regression models. What this is saying then is that this feature, W times Y at equilibrium, is just a weighted function of my peers' beliefs about Y influence my belief about Y. So this is the endogenous peer influence coefficient plus a regression coefficient that in constraint should all add up to 1 minus that of my own features. So it's a nice way of thinking about it. This really is just a network autocorrelation model. It's a spatial autocorrelation model from spatial econometrics, right? So this is the exact same thing you would run if you're trying to figure out if pollution in one county is a function of pollution in the counties next to it. If we replace W with a spatial distance matrix, you would get the exact same feature with some error onto it. There's a nice formal treatment of this that you can understand. I like this early paper by Pat Dorian. It just walks through this in great detail, and you're welcome to read that. He also gives the simple maximum likelihood sort of formulas for these things if you want to do it that way. All right, what I would want to do first is spend a little time building some intuition, because what's nice about this model is it really is a formal model, right? So it's proposing an underlying mechanism, but that mechanism might not be intuitive to everyone right at first. So let's just make up some data and see where it takes us. So in this case, what we have is a network of 3 groups. We have red, green, and yellow people. It's a clustered network, and we're going to give everyone a random opinion, right, on 2 issues. We're going to give them a random opinion on Y0 and a random opinion on X0. And these 2 things are both going to independently be influenced by the ties that you have, right? So at each iteration, the person is going to follow this model as it's described. And in order to do that, we have to set some parameters. So the parameter I'm going to set is that alpha is equal to 0.8. So that means that I'm going to fix this coefficient to be 0.8, and that means your initial position is going to be 0.2. This is the initial distribution, right? So each node, the red nodes, the green nodes, and the black nodes, I didn't have yellow, it didn't show up on the screen this way, right? So we have these 3 groups, we give them their opinions. Again, it's just random, and then at the first iteration of this process, they become more similar. So what's happened here is that I've gone from my randomness set, each person then moves to the weighted mean of their alters, and so forth. At each of 7 iterations, you can see then that the red group, the green group, and the black group, they come to take on the same opinions of each other because they've weighted their peers more closely than they would otherwise. So you end up with, from a completely random set to a structured set, entirely as a function of a peer influence outcome. You can do this in lots of different ways, right? And so here I've done it again. Now this time I've said that we're going to weight in-group ties heavier than between group ties. In the initial set, I treated this network as everybody was counted as equal, which means that this green tie is going to influence this yellow person just as much as the yellow person will. Now I'm going to shift that idea and say that if we're in the same group, I'm going to count your opinion double what I would count the opinion of somebody who's outside my group. And as you might expect, that's going to lead to a greater distinguishingness. Distinguishing is a bad word. A greater difference between the 2 sets. Now, it turns out there are lots of things you can do with this model, right? This is really the tip of the iceberg. You can play with the ways in which W is constructed. The way I've done it here, and the most common way, is a simple average. That is that the influence you have on a person is just a normalized version of the adjacency matrix. So if I spend 5 times as much of my time with you as I do with somebody else, then your opinion is going to count 5 times as much as it does the others. So if you take a weighted matrix, a weighted adjacency matrix, you row normalize it. That is, so that each row sums to 1. That then becomes your W matrix. You plug that into this formula and you estimate it. And so it's really that simple to get these outcomes out. And you're using the same kind of ways of getting these coefficients as you would if you're doing spatial regression models. The other thing that people do sometimes is you can make alpha time dependent. That is that initially I am open to lots of people's opinions, but then it shifts over time, right? So early in the time series, I'm open to influence, but pretty soon I'm going to come to an opinion, and my own opinion is going to matter more than your opinion will. I might decide that alpha differs by some other characteristic that I have. So men and women might be differential influence to others. Men are more susceptible to influence than women, or vice versa. And so you can imagine building that into the model by having the alpha coefficient interact with the different kind of features that are going on in your standard initial behavior function. And there are lots of ways you can do this. In order to get this model, right, you need to do some kind of a regression effect. The simple row normalized adjacency version is just a network autocorrelation model, and you can write down the maximum likelihood function for that, and you can estimate it directly. It's something that's implemented in R, and we have some examples of it in the course materials. You might also decide you want to just use, you can literally hijack spatial autocorrelation. If you've used spatial statistics, you can use those features. It doesn't get you around the causal problems. So the causal problems are a different subject. But in terms of getting a relatively accurate estimate, given that you specified the model correctly, you can find what the correlation is, at least that way. The other way to do it, if you don't want to use the kinds of econometric models built into spatial autoregression models, is you can use non-parametric models. And so the quadratic assignment procedure provides a nice way to just create a permutation test in which you don't make any of the assumptions about the error term. You just generate random networks based on the data that you observed. Those tend to be a little more cautious than you're less likely to have a specification error. Again, it doesn't change the causal interpretation, it just provides a different way of estimating the statistical significance. Another thing that people do a lot, and this is going to come up when we look at some of the Christakis papers and a few others, is you can switch from a difference in levels, which is the way we specified it before, to a similarity to others. So I can create a dyad level model and say that 2 points that are similar to each other, if they're tied to each other, is one way of getting this. And so there's a dyad version of this. So you have these difference. So Yij is a matrix of similarities, is a function of some intercept plus the fact that you and I are tied to each other, so we're similar to each other on our friendship, plus some features about how either I is different from J and so forth. So you can write it down that way. Substantively, these models are, so theoretically, these models are easier to talk about than they are to estimate, and certainly easier to estimate than they are to evaluate, if you will. And the best example of this is the controversy over Christakis and Fowler's work on the spread of obesity in a large network over 32 years. So you're probably familiar with this New England Journal of Medicine paper. It's got a bunch of press. They used data from the Framingham Heart study, which was a longitudinal study of about 32 years. It turns out that the data, because it was a really high saturation sample in a small geographic area, and they asked everybody to tell them a bunch of information about other people that they engaged with as a part of the sample monitoring data they collected, that they ended up implicitly collecting network data they didn't expect to collect. They had a lot of kin in the sample with each other, so they had kinship ties automatically, and they had neighbors and close contacts by virtue of the people that you would come to the survey with, or names you would give if if your address was lost or something, that kind of thing. And so they ended up then being able to find a correlation between the extent to which people are socially distant, that 1-step, 2-step, 3-step we talked about before, and how similar they were in their BMI. And this fell off pretty quickly after about 3 steps. And so it turned out being the case that they made this claim that a friend of a friend influenced my own weight gain. This was a relatively what do you call it, controversial claim. They had multiple types of relations, right? So they found that mutual friends tended to have a stronger correlation in terms of their weight behavior than did non-mutual friends, same-sex friends more than opposite-sex friends, and so forth, spouses, siblings, and so forth. Now, as you might imagine, they ended up doing this as an edgewise model. They actually did it a couple different ways. So the edgewise model was that my current weight was a function of my alter's current weight plus the alter's previous weight, my own previous weight. So a classic lagged regression kind of model. They also estimated this as an ego difference model that gave a substantively similar conclusions with both models, as you might expect. This is what the classic peer effects model looked. This ended up being, just to give them credit, this is an individual level random effects model, so they ended up having lots of ways of trying to control out unobserved features. That didn't stop the controversy, right? So there was a lot of debate about this model, and in part it was because they made some very strong claims. They used the word contagion deliberately to sort of make it clear that this was a causal claim they were making. And econometrically, it's not just, you just can't do that, right? It's these models are not identified causally because you don't have enough information necessarily in the controls here to assure that you've properly accounted for all possible upstream pathways that can create a potential for causal bias. And the best way to think about this, there's a really sort of damning paper by Shalisi and Thomas that point out that the causal effect of any kind of adjacency between I and J is going to be at risk to any upstream feature that might create an unobserved or a latent trait that leads to both friendship and behavior. And that then makes it impossible to distinguish the underlying effect of an adjacency in the set. Now, there's a couple of versions of that if you want to go through it. I'm not going to spend a lot of time on it. The key element here is that intuitively is that these types of models always suffer from a fear that there's a selection feature into a relationship that is also a feature that generates a risk for a behavior. So if it's the case that you're a risk taker, you then like other risky people because you like to do things like, ride your car fast and go to monster truck shows or whatever it is, right? So if you're have a risk, a high adrenaline kind of personality, you're going to seek out other people who are also adrenaline junkies. And that's probably going to lead you to the similar kinds of health behaviors. And if you're a couch potato and like to watch TV, you're probably likely to also select other friends that are couch potatoes and like to watch TV. And both of those, the fact that you're both friends and both end up having heart attacks might have very little to do with the fact that you're both friends and a lot to do with the fact that you both like to sit on the couch. So being able to explain these features is something that's really hard to do clearly. And the problem, of course, is that we can't distinguish these elements. Now, there are some solutions to these problems, right? The first is to come up with some kind of a way to really control for the features that are plausibly upstream. And I think this is probably the smartest solution. I encourage you, if you're interested in these models, I encourage you to read the debate that is around these particular papers. And you'll see in the slides, just hit pause, go and look up these papers or email me and I can send you the bibliography. There's a nice, there's this link here on slide 75. It has a nice set of working papers that really talk through each of these elements and why they're there, part of this debate. I think that a lot of this debate has gotten dug in with people being unreasonable on both sides. When we do some of the more careful analyses, which we're going to get to in a moment, the solution to the question, the answer to the question, is it selection or influence, is invariably yes, right? That it's both selection and influence. It's never selection or influence. And I think it's just a poorly posed question. Given though that we want to do the best we can to identify the causal effects as cleanly as possible, it is important in these models to make sure that you use well-specified and well-measured controls that allow you to identify as clearly as possible the upstream features that might create confounders on the sets, on both selection and influence. The alternative then, if you can't do that directly, is to come up with some kind of an instrument and to use an instrumental variable sort of model. I haven't seen as many, there's a fair number of hard versions of this, where you actually literally try to go to find an instrument and use that in a Heckman style or a classic instrumental variable sort model. I hope we start to see a little bit more models that use structural equation modeling to do this, because it seems to me there ought to be ways to do this with latent variables, which would be a lot cleaner. And in many ways, I suspect easier to identify, but that's just a personal aside. Or we can use models that have been directly generated create these, to disentangle these effects. And these are these dynamics, stochastic, actor-oriented models that we're going to talk about in a minute. In the absence, those are the two observational routes out of this problem, to the extent that you can get out of this problem, I guess to the extent that it's a well-posed question. The third way to do it is with experiments. And there are some moments when we have experimental opportunities, particularly with things like random roommate assignments or something like that, but they tend to be rare. And so it's, I'll talk a bit about what those are, but they are difficult to do. The common solution, particularly for people who don't spend a lot of time thinking about networks, but kind of that maybe spend a lot of time thinking about causal effects for policy, are to think about instrumental variable models. And I think the problem with instrumental variables is really general and is particularly problematic with networks because the unobserved features that create ties are so rich, right? So the things that select me into activities are so closely related to the behaviors that I engage in that disentangling them is pretty hard to do. But in general, whenever you come up with an instrument, right, you have to have the characteristic that this is the classical Ballantine or Venn diagram model of a regression coefficient, right? Recall that the effect of X on Y is the unique variance between X and Y. And what an instrumental variable model requires you to do is have something that's correlated with both X and Y, but not correlated with the confounders that might lead it into the two. And that's necessarily going to be a smaller set of the overlap between X and Y. It's just definitionally, it has to be. And that feature then is going to, the smaller this gets, the better your instrument, but also the weaker your ability to uniquely identify this effect. So we spend a lot of time, I think, the harder we search for instruments, the more time we spend doing essentially, low-powered tests that are going to bias us towards null effects. So I encourage you to be a little less worried about the instrumental effects and think more about your design and your theory, and getting sure that you have good observational data to do it. And we'll talk some more about some of that in a second. The other feature that I really like, that I think do these really well, are to spend a little bit of time thinking about sensitivity analyses. So I think that we can have a good case for theory, right? You have to have a theory that makes it clear that these things are there. You have to have time order. You have to have good causal selection features. I think you want to be able to model both friendship patterns and outcomes simultaneously. I think this is the best bet overall, and models that do this are there. They're just not as often used as you might expect they are. But really, at the end of the day, if you're the kind of person that thinks there's a selection feature that's driving these outcomes, I'm probably not going to be able to convince you that my either my instruments or my modeling solution are effective in this. So I think the best solution are sensitivity analyses. I think it's the most pragmatic solution to get out of these. And this is to ask, to take seriously the notion that there can be confounders and they're observed, and then ask yourself, well, how big a confounders do these really have to be? Ken Frank has done a really nice job on these. Tyler Vanderweel has also done a very nice job on these kinds of models. And to me, this is probably the simplest problem out of what is otherwise an intractable set. And if you're making a claim, particularly a policy claim or an intervention claim on a network, and your estimates are really sensitive to the way the model's been specified or potential outlying variables, then you're in trouble. But so long as your estimates are really robust and strong, I think that you might have overestimated a coefficient. That's always possible. But the fact that it's going to go away entirely is probably going to be pretty small. And these types of sensitivity analysis, I think, pragmatically, are your best way to go. This is a screenshot of Ken Frank's work. I strongly recommend his software just because it's so easy to use. If this is the kind of direction you want to go, I recommend you go there. The other way out of it, again, just to circle back, is to think about these simultaneous models where you're simultaneously modeling the friendship structure and the peer influence structure. To get there, we have to figure out how you model friendship structure well, or model the relational structure well. And that's going to take us down a bit of a rabbit hole where we can come back to the actual health outcome we care about in this case, which is these joint models for actors' behavior and friendship relations. In order to get that, we need to think about how you model friendships. And that's going to take us to questions about random graphs. All right. The random graph models are the solution to the question, where do networks come from? So if I want to model networks statistically, I need some tools, some machinery to get there. And the classic regression machinery isn't generally effective. You need something slightly different to deal with the kind of nonlinearities and massive dependencies that occur inside of network structures. And to do that, we come at it from a position of random graph theory. And the history of random graph theory is long, it's rich, it's really interesting. We're not going to spend time talking about the whole thing. I'm going to introduce you a little bit to random graphs just to give you a sense of what those things are. Then we're going to jump straight over here to ergoms, right? We're going to nod our head at latent space models, and then we're going to end up right down over here at Siena models. And so that's where we're going at the end of the day. These are the network autocorrelation models we were just talking about. They're a subset of these kinds of features. All right. So the network inference question ends up being a little bit different. There are a couple ways to set it. What we're used to thinking about in terms of like a t-test or something is to say, well, can I generalize from the observed score to a sample population? One of the assumptions of network analysis is you have the population. So there's a snarky answer to these kinds of inference questions, which is to say, well, I don't have a inference problem because I don't have an inference situation. If you've observed the population, there's no sense trying to make an inference question. The, of course, response to that is that on any given day, you've sampled the network and it might change the next day. But that is a subtle shift in the question being asked about what inference we're trying to make. And the question that we typically ask from an inference on the features that drive an observed graph, or would we see the observed graph if the process generating that graph were random, or to be more careful, if the process were conditionally random. That is, if we saw some features fixed, but was otherwise a random set. So common association tests assume a case independence. Ours does not do that, right? We can't assume case independence because the whole notion of saying that a tie is more likely if a friend of a friend is a friend is that they're no longer independent. And so we need to think about ways in which we can get to samples that lead us to away from this independence assumption. So one way to do this would be to say, well, I've observed a network. Let's see how that network compares to all the networks out there that are like the one that I have, to say the same number of ties and the same number of links. The problem is the number of those possible graphs grows really fast, really big. And so what you want to do is, what you'd like to do is enumerate all the graphs that look like the one you have, at least in some features, but that enumeration problem is impossible. And so instead we need some way to get at an enumeration like inference without actually having to enumerate all possible graphs. And we do that by assuming a randomized process. And so the Erdos-Rani graph, Erdos-Rani graph, I can't speak today. The Erdos-Rani graph is one in which you assume that there is a coin flip probability, that I take the network, right, on each dyad, I flip a coin, and I flip a coin weighted with some probability. And that probability then gives me the likelihood of an edge or not. And if I do that across all edges independently, I get a simple Erdos-Rani graph, Erdos-Rani random graph. And this is an example of just a simple random graph. What you find is that if you think about the size of the largest component, if I just allow the average degree in my random graph to go up, that is, I change that probability of flipping a tie, you're going to see this kind of rapid shift into a phase transition from no one connected to almost everyone connected. And this is a classic element of a random graph. And this is why our inference about what happens with degree and what happens with something like the connectivity or the risk for a disease spread in the network is usually wrong. It's because you have these kinds of sharp breaks and transitions that you wouldn't otherwise see. All right. So the simple random graph tends to be a very poor model for the network. That is, so I can imagine just saying, let's take my graph, I compare it to a graph with the same number of nodes and edges, but I've just flipped a coin instead of looking at the random graph and see if they match. They're never going to match because real life is not that. So instead we might say, let's make a conditional random graph. So here's an example. Right? I've observed, this is one of the ad health networks, I've observed ties between kids, whether they're white kids, black kids, or mixed another race. And you can see that there's a mixing probability. So the probability that white kids mix with white kids is about 0.009. Probability that white kids mix with black kids is about 0.0016, right? So you have a higher likelihood, about double, about almost 9 times as likely to mix internal as opposed to external. So what I could do is generate a random graph that has this exact same mixing matrix. And I do that, it looks something like this. And you can just see by eyeballing it, right? It just doesn't match the eyeball test. That in this case, we've matched the mixing matrix exactly, right? But there's some other feature that's driving the patterns of ties in this networks other than racial mixing. And we can look at that instead by saying, let's look at the degree distributions. So the observed tie versus the random tie. The observed network has this much longer tail. There are a few kids out here that have many more ties than everyone else. So what we might want to do instead is say, let's make it mix not just on race, but race and degree. And so you can continue to try to do that. It's a fun little sort of output here that we can think about in terms of random mixing. I'm going to leave that aside from now. So just ignore that. That's the problem with doing this recording is you can't ask questions. So we're going to compare multiple networks now. So one of the advantages we get out of random mixing is that you can see what kind of where this is going. And this is the intuition that we're going to try to build around testing random networks. And so to do it, what we do is we take an observed feature of the network and we compare it to some suitably constrained random network. Now, suitably constrained here is a heavily loaded term, but just we're going to bear with me for a moment. And so if we can do that, we can compare our observed network to a suitably constrained random network. We can assess the extent to which those constraints, those things that we're constraining our random network to, account for the things we've observed in our real network. If these two curves were pretty close, like if they were very different, if we had no racial mixing, but a lot closer when we added racial mixing, then we could say that racial mixing accounts for a good deal of the structure in this network. And we'll have some more formal ways of saying that in a moment. So one way of doing that is to do something called the quadratic assignment procedure, or a permutation test, in which we can imagine asking a question about an association on a network or a pattern on a network, and then compare that to that same association at random. And so in this case, QAP is done by taking, we're going to ask ourselves whether or not the marriage ties in this particular community correlate with the business ties in this community at a level greater than we'd expect by chance. So these are Italians in the medieval ages. This is the Medici data from Paget. What we see then is that if we correlate, are you married with do you do business, you get a correlation of about 0.37 and change. That correlation seems big, but is it more than you'd expect by chance? Well, to find out, what we do is we first take the observed case, 0.37, we just correlate marriage with business. Then we take the business network and we randomly shuffle it and do the correlation again. Randomly shuffle it, do it the correlation again. Randomly shuffle, do it again. Do this over and over again, and you recalculate the correlation and store it. And what you're going to get is a distribution of correlation coefficients, right, from the observed data. And you can compare that to your observed data, or from the randomized data to your observed data. And that comparison allows you to figure out whether or not you would have observed the correlation you've seen from a random data. And this is the logic that underlies a lot of the graph statistics we're going to play with. Now, they're not always done with a permutation test, right? But it's a comparison of a fixed feature with an ensemble of features. In this case, it's an ensemble of random graphs that you've generated by permutation, but it might be an ensemble of random graphs that we know mathematically because of an underlying distribution that has to do with, say, the degree distribution or something. So there are ways of getting that. It turns out that from random graph theory, there's a lot of way to get configured random graph summary statistics without actually having to go through and generate the whole thing. And that's one of the things that we've been able to learn in the last 20 years about studying random graphs. So how do we do it? One way we do it is to get at these things called exponential random graph networks or other kind of models for networks. And the intuition here that I think is a place to start, it's backwards. I'm just going to say that to start with, but I think it'll help you think about it, is to start by imagine a logit model, because we all grow up in social sciences thinking about logits. It's a nice way to build some intuition about things. So imagine your adjacency matrix. I built a version over here. On this graph, and I'm going to specify it as a heat map, whereas blue ties have very low probability, observed ties have are red, they have a high probability. And so for the observed network, it's binary. You're either observed or not. So it's either a tie or it's not. It's either a tie or it's not. We're going the diagonal. And this is what the observed data are. And we might imagine modeling this as a function of some features, right? And the features we're going to model it as a function of are a simple intercept. Let's just start with that, pretend that doesn't exist. But that's saying is that the probability of a tie between I and j is just equal to some function of some simple constant. If it's a constant, that means it's all you have is density, right? So what I can say is that my best guess, if I knew nothing else about what causes a tie in a network, I'd say that given the density of this network is 0.24, everyone has a single probability of being hit. That's what it's at. And you'll see then that this network has an even probability. It doesn't fit very well. If you exponentiate minus 1.13, you'll get the density in this case. That works out kind of nicely. Let's say, well, instead of just density, we're going to add a feature of the sender. So the I have my coefficients backwards. I apologize for that. All right, so it's a row feature in this case, or a sender effect. And this is going to be a sender's degree. So in this case, a person who has 5 ties should have a higher probability than a person that has 1 tie. But notice that everybody that has 1 tie are going to be the same shade. So this model predicts the same outcome because the only information is the overall density adjusted for the out degree. And so that's a sender and a degree-based piece. We can flip that around and say columns only, right? So now people who are receiving, and you see where this is going, of course. We might just say that there's both sender and receiver effects. Now this does a pretty nice job. Right? In this case, we find that the bolded ties are the ones that are actual really ties. And we can see that we end up with that those tend to be high probability ties, i.e. the red ones are high probability. But you'll notice that you see some of these blue ones were real ties, but they're not there. And that might be because we're missing something. There might be some other quality that creates I and J that makes it much more likely that they might be the same race, they might be in the same grade, like any of these kinds of things. So some dyadic similarity here creates a high probability of a tie. Again, it's not always perfect, right? There's going to be cases where we miss, right? Either having false positives or false negatives. The intuition with this then is that if we can build these models as a function of the features of senders, receivers, and dyads, we can think about the collection of networks as a result of these underlying dyadic processes. Now, the key twist on this simple model is that the logit model focuses on dyads, whereas the exponential random graph framework says that you can't think about this as a logit problem exactly. Rather, the logit is an instrument. It's a tool to get you to a collection of graphs that are defined by the coefficients on these processes, on these models. So what happens is, if we just go back up here a minute, is that we've now written down a probability function on the space of dyads, and that probability set on the space of dyads then defines a kind of Bernoulli graph, right? It's like having the mixing matrix I showed you before, where we had whites, blacks, and others, right? But now instead of whites, blacks, and others, we have the entire multidimensional set as defined by our observed variables in this logit space. And so that defines a set of differential weights in the space that you can flip coins with that are going to create a network that is conditionally random. It's conditioned on the features you built into the graph. And that then defines an ensemble of all possible graphs, that is the class of all random graphs with the given known elements, right? And we can then ask how likely it is that our observed graph came from that ensemble of graphs. And so that's how these two things fit together, right? So if I specify a model that's based on degree distributions and matching on grade, say, if it's a high school network, and my network still doesn't fit very well, then I know that I haven't, at minimum, I haven't identified the features that could have given rise to the graph I've observed. And so this is a little bit different than a lot of the hypothesis testing we're used to, in the sense that what you're trying to do is fit the graph with the minimum set of features that you think are driving the outcome. It ends up being the case that to get to this ensemble of graphs, the key element is that the standard errors that go with running this kind of dyadic logit model are garbage. You can't do that. That's where it falls apart. But the estimates themselves are actually quite informative if you specify these statistics, these row features and these column features and these dyadic features very carefully. And that's done on an area under the hood that I'm not going to have time to get to today because of the short feature we're going on. But there's a set of theorems that allow you to explain how using change statistics on the network can give rise to an estimable probability of the underlying ensemble of graphs. And it allows us to treat networks and the explanation of networks much the same way we would with this logistic intuition. Okay. So there's a history of this. The original model of this sort was the P1 model by Holland and Linhart. This came out in the late 60s. It was a log linear model that I've written down here as a logit model, but it's the probability that a tie between I and j is equal to 1 is a function of sender effects, receiver effects, and reciprocity. You can estimate those models directly. There are lots of other ways you can play with this model, and once you had this model in place, you can do lots of different things. And so this was a pretty standard way of doing models for a while. Then we all just sort of held our nose and dealt with the fact that these were approximate standard errors. What's come up since is a nice set of work, and this is coming out of statistics. The work that I'm building off here is coming out of the StatNet teams, but the Stanley Wasserman and his P-star models are one of the first people to come out with this sort of that's the modern version of this set, to show that you could specify the probability that the observed graph is a member of the ensemble of all graphs defined by your model as a function of the observed statistics and some coefficients normalized by some underlying constant defined on the set of coefficients. And this is the key, is that to being able to get this exponential random graph framework, you need a normalizing constant. That normalizing constant ends up being impossible to specify directly for any kind of graph that's at all complicated, but you can do it as a function of a change statistics on these underlying graphs. So if these are features of the graph model, like transitivity or reciprocity or something like this, you can then take the difference between what would happen if the tie was forced to be present versus what the tie was forced to be absent. That change score ends up being the complement of the overall graph, which makes it possible to get away from an even estimate of your coefficients without having to estimate this underlying constant. And that's a nice trick, and that's kind of fun. In practice, these are still pretty difficult to estimate. So what you end up doing is you use an MCMC, Markov chain Monte Carlo. I've just been talking too long today to fit these models. And that's essentially what you're doing. If you think about what we're trying to do with these models, is you're defining this probability space for each die in the network. You're trying a set of parameters that would define a coefficient. You're flipping the coin, seeing how well that defined Markov space, that set of coefficients, fits the graph that you've generates a probability distribution that fits the graph that you've observed. If it's nice, if you have relatively a lot of consonant sort of high red values in places where there are really ties and low blue values where there aren't ties, to the extent that that's typically true, then you fit the observed statistic. And so we want to keep adjusting that parameter as you go, and that's done by this MCMC chain, sort of working through on the coefficients until you can't get any better. The models are fit in R. We have some examples in the software that's posted on the site. You're welcome to run through those and have a look at them. The nice thing about these models is that there are lots of features that you can fit. From a health standpoint, the ones that typically matter the most for us are these homophily features. So is it the case that smokers hang out with smokers, or drinkers hang out with smokers, or what have you? And so there's a whole set of node match terms that you can fit. While holding constant a lot of the features that might otherwise be messing up your estimation of these kinds of homophily features, such as transitivity. And that's one of the key ways in which we're able to estimate health relevant associations on graphs while holding constant some of these friendship selection things. So it might be that you and I hang out together because we both smoke, or it might be that we both have similar friends, and you can, in a classic regression sense, control for one of these as opposed to the other. The nice thing about these models is that they allow you to include all of these kinds of features. The difficult with them is that it's really easy to specify nonsensical models. That is, I'm going to go back to this slide here, and I apologize for if you're getting whiplash watching me go back and forth. But what you're doing is you're specifying a model, right, that defines a probability space for the graph. And this model is going to have some kind of set of coefficients that then translate by the logit equation, right, to some set of probabilities on the edges. The problem is that these coefficients are linear on the logit scale, and I didn't write this right, but if you did it this way, these coefficients, it's a classic linear model, right? And what our intuition is going to tell us about linear models are that if you have a little bit of something and a positive effect, and a lot of that is even better, right? So if we can imagine a triangle effect on the graph, we might say that a friend of a friend should be a friend. And so from a regression standpoint, you can imagine putting that in your model. And I expect to see a positive coefficient. And the positive coefficient says that the more often I have a closed triad, right, the more likely that this edge would create a closed triad, the more likely I am to make that edge. That's a perfectly reasonable thing, and just like we'd expect, the more education, the richer you get, right? That's our intuition from regression. The problem is these models have that nonlinear flip to them, right? And what these models are saying is that if a little bit of transitivity is good, is that if a friend of a friend is a friend, and we see that fairly often in these sets, then we ought to see it all the time. And so it's really easy for these models to quickly tip into these things that are called degenerate spaces, that where everyone is in all the probability mass is on a very, very small part of the underlying distribution. And we might think of this as an error in the models, that there's something about this MC-MC chain that's not converging right or something like this, but really not. It's a model, it's a problem with the specification of the model, that in fact, we don't behave in the social world that a friend of a friend is a friend. A friend of some of my friends are my friends. And we don't have infinite capacity as people to be friends with everyone. And what that means is that we're forced, by virtue of just not having infinite time, to have a diminishing marginal return to something like transitivity. So I like that my friends are friends with each other, but an acquaintance of an acquaintance is not going to be a friend. And so it's going to be vary by the extent to which I can have these types of things happen. And so it's taken the field a long time to learn how to specify these models accurately. And so there's a term now, for example, called the geometrically weighted edgewise shared partners. This GWESP term, as it's called, is really just it's a marginally declining return to the investment in triads and the probability of an edge. And that is an accurate way of thinking about the way that each additional edge or each additional closed triad is going to lead to a probability of an edge. All right. Part of the problem, so what this is a really complicated way, and I'm mad at myself for trying to talk about this so quickly, but what this is really helping us to, what I'm hoping you see out of this is that the good news about ergms is that you can specify lots of different features about a graph, be there the way in which the structural feature is going to give rise to a tie within your network, including, for health purposes, most of the homophily features or friend of a friend kind of features that we care about. I want you to take away that it's got to be specified accurately, that these models are sensitive to misspecification, particularly for any endogenous parameters. It's really easy for those endogenous parameters to rapidly close in on themselves in ways that your intuition might not help you understand. And so in order to do that, you want to think carefully about how you specify your models. Simple models are better than complex models, but read the literature and see what people have done with these kind of models and build on those kinds of well-specified models so you think carefully about this kind of snowballing effect that you might have. Now, one side effect, one way to sidestep this problem is to say, well, I don't really care about the detail and structure of the network. It might be the case that friends of friends are friends. It might be that there's a latent feature that drives people to be friends with each other. I don't care. What I want to do is control for the network structure so that I can really test whether or not smokers are more likely to be friends with each other than non-smokers, net of any other kind of feature that might be there. I think the best solution to those kinds of models are what are called latent space models. And latent space models are models where you assume the same kind of probability structure that we talked about before. This is, again, a logit space underlying the hood here. But what's happening is the probability that I and J are friends, conditional and everything else, is a function of their distance in this latent space, whereas Z, in this case, is some unspecified, unknowable, undefinable space, social space, that is monotonically associated with the likelihood of us being friends. The closer we are into social space, the more likely we are to be friends. And of course, you can have multiple dimensions to this. So it might be a 2-dimensional space, it might be a 9-dimensional space, it doesn't really matter. And we don't specify what this is explicitly. It's not an observed variable, it's an unobserved variable. But it's chosen so as to maximize the likelihood of a fit, right? And it's going to find the best 2-dimensional fit, or the best 3-dimensional fit, or the best 25-dimensional fit to the data that you decide to put there. And then you can ask, net of everything that I can put in the model unobserved, do any of my observed characteristics still matter? All right, and this is a tough test, right? Because I've already given everything to the machine. But it does let you say, is there any variance? So if your really goal is to control for the unobservables, this is a way to let the machine do that for you. And I think it's a good way if you really don't care substantively about explaining the source of structural variation in your network, but you just want to control for the structural variation. These linear models, or these latent space models, excuse me, are great for that. This is just an example of the output from one of these kinds of models, right? So this is the observed network and the latent space model. There's some stochastic elements in this particular version of it. And so the position of nodes 17 to 18 to 19 here heavily overlap in this particular area. And you can see that there's a Gaussian distribution of their position in these 2-dimensional latent space. It's a really nice model, and you can add to it lots of different outcomes, and they're easy to fit. Skip over that. A more complicated version of these models is the additive and multiplicative effects models by Hoffman and Bolfoski. These are really flexible models. They are essentially melding both the latent space version and the observed row column dyadic homophily effects that you get out of the ergo model. So it's a generalization of both of these kinds of features, done really slickly. The latent multiplicative covariance effect here in this feature allows you to fit all those latent features while you're still fitting all of your row and column effects, either attributes or volume effects. And so it's really nice to do. The problem with this model is to the extent that there is a problem with it is that it is computationally intensive. So it will take a while to estimate. If you have a big network, it's going to be a little bit slow to fit. So I encourage you to be a little careful on that. But it's a nice package for it, and it runs quite quickly. Right. I probably should have put these ahead of time, but now we have, just to back up and tell you where we're at, right? So we have these two elements. We have, on the one hand, we have the network autocorrelation model because we care about peer effects. The problem with estimating peer effects is we don't know if there might also be selection effects. We needed a set of models that help us understand where the networks come from. That's what the ergms do for us. And where that's going to take us at the end is the ability to simultaneously model both networks and behaviors. Before I go there, I want to spend just a brief moment, like literally 2 or 3 slides here, to show you that there's an alternative model to disentangling selection and influence, and that's to use network interventions, that is to use experiments. Now you can do this observationally if you're lucky and you find some natural experiment like random roommate assignments where there's something induces a social tie, and then you can ask whether or not that induced social tie also later creates a correlation in behavior. That would be a nice randomized sort of natural experiment. Or you can generate them, right? So you might be the case that you have the capacity either through an online experiment or through because you have some control of assigning people to workplaces or what have you to randomize their assignment to each other. These are good for assessing the effects of peers on outcomes. The flip side is to take them as true, and this is what Tom Valente has done. He's much less concerned with the causal effects debate that folks have with the Christophel model than he is with taking what he believes to be the preponderance of evidence, and I would agree with him, the preponderance of evidence for strong causal effects of networks on behavior, and instead asks, how do I manipulate those directly? And so he has a beautiful paper that outlines the 4 classic types of interventions that one can do in a network, and particularly for those of you that are interested in health outcomes, I strongly encourage you to go and find this paper. It's titled Network Intervention, so it's really easy to find. It's a science paper, and he defines these 4 features. You either focus on individuals, that is, you identify, for example, peer leaders or key players that you then see with a bit of information or a health intervention, and they take that out to their peers. Alternatively, you segment the network in one way or another, so you find natural clusters in the network and you give a treatment to one segment and not to the other. You might induce ties between elements that are not otherwise there, so you enhance relations and communications. So we know that nodes 26 and 23 in this particular example already talk, but they're both good at something, so let's make them talk to each other more often. Or you alter the network. You try to create ties that might not otherwise be there. He's had a really good luck with lots of these types of outcomes. I'm not going to spend a good deal of time talking about these in detail, other than to point you to them and say, look, there's lots of opportunities here to use network interventions to induce outcomes that come with a natural sort of ability, because you're controlling the intervention, to have an experimental control as you do it. So there's lots of opportunities to do it that way, which I think is often cleaner than any of the observational methods that we're doing otherwise. All right. So a brief aside away, back to trying to distinguish stochastic actor-oriented models, or Siena models, from the rest of our outcomes. So the way these work is that we're going to simultaneously model the network and the behavior. And you can think about this, for those of you that are sort of a little social psychological background, from a classic Hyder social balance idea. So in this case, I have behaviors linked with black arrows and associations with green arrows. And so it's the case that person 1 is friends with person 2 is friends with person 3, persons 2 and 3 play chess, persons 1 and 2 both drink, 1 smokes, and no one else does. And then at time 2, we see that persons 1 and 3 have become friends, 1 has stopped smoking, all 3 of them now are drinking. Is this evidence for selection or influence? That would be the question you want to ask yourself. Now, we could make an argument that this is the case, that because everyone here becomes friends, a friend of a friend becomes a friend, that's a good indication that people who didn't used to be similar now became friends. They also started to drink together. It might be, though, that there's something about being a chess player that leads people to drink, or something about smoking that leads you to drink. And once we started drinking, that makes us likely to be friends together. The fact that we've all simultaneously started drinking and started smoking, or started becoming friends with each other, means that we can't know by itself which of these features is driving the outcome. And so what Siena models try to do is to say that effectively what we're deciding here is that each actor has some implicit utility. There's some value to smoking, there's some value to drinking, and there's also some value to being friends with each of these people. And so each person is, controller of their own destiny with respect to who they hang out with and what they do, and they're going to do the things that maximize their utility. That's the underlying logic of these models. And so we can specify it as 2 separate equations. So we can have, on the one hand, a network change utility that says the utility to actor I for engaging in some network behavior, some network function X, is a feature of the set of coefficients, the state of the network, right? So we have all of those built up here, plus a series of errors. And so this is the network change utility function. And there's simultaneously a behavior change function. And these 2 functions are estimated simultaneously to say that, all right, actor 1 is going to go through and it's going to look at all possible outcomes in the times between time 1 and time 2 that are unobserved, an unobserved latent time period where there's some amount of change that occurs. And we're going to say, can we find a set of coefficients to these 2 utility functions that are homogeneous across all actors? So all actors with the same set of, that in the same situation behave the same way. That's one of the assumptions of the model. But no, you can specify your conditions pretty generally, so that's not too strong of an assumption. Can we find a set of equations, a set of coefficients that create a really good fit in simulation between the state of the network at time 1 and the state of the network at time 2? If we do, right, we optimize this network, we keep doing that over and over and over again, we're going to find a set of coefficients to do it, and that's going to give us the ability to directly contrast the coefficients for a network formation feature and for a change in behavior feature. So these 2 things together then allow you to simultaneously estimate a influence parameter, that is, if there's a homophily, a friend of mine as a smoker, for example, might change my smoking behavior, or a selection feature, a friend who's different from me in terms of, or like me in terms of smoking, creates the likelihood of a tie. What these models are exploiting under the hood are temporal asymmetries in behavior outcomes and friendship outcomes. And so to the extent that one of these precedes the other is a little more often than they might otherwise, or people move from one state to the other state more likely than they do from the first state to the second, that then creates a moment to identify these features. They're very slick models. They work again by a Markov chain model. Essentially, you just create a little micro simulation where each actor is given a set of initialized parameters, and then you adjust those parameters to see on the equation as specified through this loop to see if you've met the best possible interpolation between the time one network and the time two network. And at the end of the day, it spits out for you two nice equations that really do a nice job. That will give you an answer to the likelihood that this was a selection effect or an influence effect. Conditional on having specified the equations correctly. So that is the case that just like any other explicit two equation model, it is assuming that you have an accurately specified model. So if there's some third feature unobserved that's not part of this network that is causing both of these features that you haven't been able to account for, then it's not there. But to the degree that you can simultaneously exploit observable information on both the behavior and the network, this does a really nice job of interpolating between those two. That said, they're computationally intensive models. They take a long time to estimate, and they're a little finicky. There's a relatively high level of constraints in the ways that you have to use these models, right? So you have to, your behavior has to be ideally binary, not more than ordinal. And if ordinal, a smaller number of categories is better than a large number of categories. Your network needs to be moderately sized, on the order of thousands it can do, but it can't do hundreds of thousands. And thousands, you better be patient, right? There needs to be some change between the ways, but not too much change. And this is probably the biggest problem, is that these models can be really finicky to the amount of change. And the reason is that they have to interpret, they have to compose, make up an interpolation process at the agent level between your observed waves. And if there's no correspondence between wave one and wave two, there's just no meat for them to chew on to create that interpolation to identify those coefficients. On the other hand, if there's too much change, then there's nothing that's going to create a similarity either. So you have to balance these two, and that can often lead to convergence problems. So you got to play careful with these. All right, so that was the world's. You've now gotten a week's worth of social network and health information in less than 4 hours, roughly. So I think the sense now is I want to spend just a minute to give you a sense of sort of where I think the field is going next and what kind of things we can spend a little time working on, just briefly for some open problems. I'm going to do it because I like things to be symmetric. I have 3 problems and 3 sub-problems. And so on the methods front, I think that there's a lot of work we can do on large-scale dynamic diffusion. If you were to go through and predict a model from an SEIR or any of our sort of network exchange models that we have for simulation, what you typically expect to see is a sinusoidal curve, it starts low, rises quickly and levels off. That's not what real epidemics look like, right? If you look at the COVID epidemic, for example, we see this massive feedback between behaviors, policies, and outcomes that create these weird curves. And being able to fit those kinds of curves in real time is something that we don't really do very well yet. There are some models that are doing it, right? So we have models that are predicting COVID in the future. They're not in principle models, they're somewhat ad hoc. That is, we just keep adding compartments to our compartmental models and keep adjusting the coefficients on the fly and try to make them fit. And so the ideal model would have some principled way, kind of like the stochastic actor-oriented models, to do these things simultaneously. And I think there's a great deal of work that we can do to make that happen better. I think that missing data is a huge problem with networks that is still as yet unsolved. There's a series of papers that myself, Jess Smith, and Jonathan Morgan have worked on this. The 3rd version of this paper on interpolation models is coming out shortly. But one of the main assumptions of network data are that you have complete data. And so being able to deal with missing data or incomplete data, either by design or random, is something that would be a great deal of work that I think could spend some more time on. It would be nice to be able to bound some of these causal questions. I think that we've spent a lot of ink over the last 40 years. We've been working on the selection or influence problem as such since at least Kandel's work in the mid-1970s. And so those of us that have spent a lot of time in this work are kind of bored of the question, just to be brutally honest. Because the answer is always both. And what that tells me is that we've misasked this question. That is that the co-constitution of peers and behavior is not equal probably to a peer effect plus a behavior effect, right? These things aren't necessarily separable in real life, because in real life, social life is overdetermined. We do things simultaneously, we discover things simultaneously, and the endogenous features of social life are not a problem to be solved, but a feature that to be embraced. I don't think our methods do that particularly well. And so I think finding methods that can bound these causal questions that more accurately capture the real indigeneity, as opposed to trying to force a fake separation between selection and influence, are going to be better. And I would encourage us to try to find those kinds of methods. I don't have a solution for that yet. I think SOMs work that way in theory, but they're still sort of playing more to the separable hand than I think that actual behaviors do. That then raises a whole series of questions about what networks are theoretically. And again, I really encourage people to spend a little bit more time thinking about these roles and multiplex network dynamics. Positional models are fundamentally underdeveloped. We haven't really spent a lot of time thinking about block modeling and multi-relational models that much since Harrison White's early work on it. It's bubbled to the surface here and there, but there are lots of fun questions to be thinking about these things with. So for example, these are data on multiple relations in Indian villages that Manoj Monahan and I have collected. And it'd be really fun to think about collections of networks in this ways, in the ways in which rules of village life govern the ways in which behaviors and acceptable activities might engage in these networks. And so I encourage us to think about these in new ways that we haven't already done. The other thing that'd be fun to think about a little bit is sort of the life history of networks and network evolution. We tend to right now have a series of base models that are encapsulated in ergoms, for example, that help us think about the endogenous formation of social networks, so that a friend of a friend should be a friend, or that popular people should become more popular. But I don't think we have a good substantive theory of how relationships are developmentally constrained. That is, we don't expect a 4-year-old and a 14-year-old to engage in the same way to their parents or to neighbors and so forth. And nor should they, right? But our models expect that that's the case. It might have slightly different coefficients, but they're not playing it in fundamentally different ways. And my guess is that we could be more nuanced in that and find a way to think about that carefully. Similarly, there are real health mechanisms that get inside the heads of people that link networks to behaviors. And so if you think about the friendship in the Framingham studies, these studies were really focused on a pretty simple contagion model, and it's a passive response to the activities of my peers. My guess is that there's a much more active feature of this, and this ties right back up to the bounding causal questions. And so thinking particularly about health mechanisms, like what is it about the things that my friends do that leads to smoking that might not lead to drinking? Like how do the actual health outcomes differ depending on their etiology, the things that they do for people and how they're reflected in networks. I think there's a series of questions we can ask about data. I would love to see a return to community studies to get a more holistic view of networks. This was a beautiful way of thinking about networks in the 30s and 40s. This image that I'm showing you on the screen is from a study that was done in 1936, if I remember correctly. And these were family visit ties, and the size of the whole point of this study was that there was a status hierarchy in these communities that really strongly governed the social relationships that was there. I suspect that in large modern anomic societies that kind of a status structure is not nearly as clear as it was in villages then. But there's probably still some kind of community that we need to think about, either neighborhoods or schools or organizations or so forth. That would be a fun way to think about a setting in total, to have a holistic understanding of that again. And that might be a new way to sort of come back now that we have better tools to community studies in ways that we didn't have before. I think we would learn something if we have a chance to do some of that work. One way to get at this is going to be through electronic traces. This is happening to us already. We might not like to think of, collaring people. Radio collars is how ecologists have worked with animals for years. But we've already all put a radio collar in our pocket and let Google and other sort of, social media companies and social companies use our data. So we might as well find a way to use that data for the betterment of health and health systems. And I think that we can do this. I think the question is how we do it smartly. There are good ways to collect these data, and I think that if we can find ways to help people use that data in a way that's both ethical and beneficial to us, that's a new frontier. And it's going to tie directly with the growing amounts of electronic medical records data. This is a map of physicians. Each physician across every part of this little map in the network are tied to a patient, share a patient with a physician in Ohio, which is kind of mind-boggling to recognize that the entire national system that every physician in the country is tied through one step, right? Share a patient with somebody in each of these places, share a patient with somebody in Ohio is kind of remarkable and speaks to how deeply interconnected our health systems are. That data to understand those interconnections exist. They're already there in electronic medical records. They're not being used in this kind of systematic way. They tend to be used in a much more piecemeal way within a particular organization. And that's great. There's lots of work that I think that's left to be done there that it could be used in a really fun network way. But I think there's a bigger question about a national health system that's already been built intuitively that we're not necessarily studying. And it would be nice to open the door to that and see it some. So again, thank you for your attention on this. This has been a lot of material in a short amount of time, despite the fact this is probably the longest of the didactic sessions that are there. For those of you that are interested in hands-on how as opposed to the what and the why, check out some of the labs that have been posted. Those will at least give you a sense of what the code looks like and let you play with some data. If you have some other questions or want to dig into this in more detail, send me an email and I'll be happy to get you hooked up with our wider week-long system. In the meantime, everyone stay safe, and I look forward to seeing you in the workshop.